This is a basic fuel system. Its purpose is to store, then deliver a combustible mixture of fuel and air to the engine cylinders. The fuel system components that we will examine are the fuel tank, fuel line, fuel pump, fuel and air filters, and we'll get into basic carburetor theory too. Starting with the fuel tank, there's more to this tank than meets the eye. Internally, baffles are built in to help prevent fuel from sloshing about. Then there's an expansion dome or trapped airspace which provides room for fuel expansion at higher temperatures. Located in the fuel tank is a filter that prevents contaminants from entering the fuel line. Fuel passes through the filter and pickup tube into the fuel line. Fuel is also returned through the pickup assembly to the fuel tank. We'll discuss the fuel return system in more detail shortly. The fuel tank vent lines, filler hose, vent hose, and fuel lines have added length at the rear of the vehicle to guard against lines becoming disengaged in a crash. Some filler caps have a rollover check valve to prevent fuel leaking from the tank in a rollover accident. The next major component in following fuel flow from the tank to the engine is the fuel pump. And here's how it works. The lever return spring holds the fuel pump actuating lever in constant contact with an eccentric on the camshaft. As the end of the actuating lever moves upward, the other end pulls the fuel diaphragm downward. This action closes the outlet valve and enlarges the fuel chamber. Fuel is drawn from the tank through the open inlet valve into the fuel chamber. The fuel pump delivers fuel to the carburetor only when the pressure at the outlet valve is less than the pressure maintained by the calibrated diaphragm spring. So when the carburetor float needle valve opens, the diaphragm spring expands to close the inlet valve and forces fuel through the open outlet valve. From the fuel pump, fuel passes through this inline fuel filter. This filter protects the carburetor from contaminants that may be present in the fuel. These contaminants include water, scale, rust, and dirt. The fuel filter is also part of the fuel return system. It has an outlet nipple that connects to the fuel return line, which is connected to the fuel tank sending unit. During normal operation, when underhood temperatures are high, fuel in the heated steel line between the fuel pump and carburetor can boil and vaporize. The fuel return line does two things. First, it allows constant fuel flow, which helps cool the lines and reduce vaporization. And second, if vaporization does occur, the vaporized fuel returns to the tank and is not passed to the carburetor. The air filter primarily prevents airborne contaminants and abrasives from entering the engine. It helps reduce air noise rushing through the carburetor and also acts as a flame arrestor in case of carburetor backfire. Service is important because a dirty or clogged air filter will restrict airflow, causing performance and fuel consumption problems. The carburetor is the last and perhaps the most important part of the fuel system. Its primary function is to properly mix and deliver fuel and air to meet engine requirements under different driving conditions. This graph shows engine fuel requirements for idle and low-speed operation, cruising, called main metering in the carburetor, and power enrichment for high-speed or full load operation. The carburetor automatically leans or enriches the air-fuel ratio to meet these operating needs. Let's examine the inner working of a typical carburetor and see what happens and how. We'll discuss carburetor theory and service symptoms. With minor variations, all carburetors use a pressure difference principle to deliver fuel to the engine combustion chamber. This bug spray illustrates the point. The container is vented to the atmosphere. Pushing the handle forces air through the nozzle at high speed, creating a low pressure area over the pickup tube. Fluids flow from high to low pressure areas. Therefore, fluid moves up the pickup tube, mixing with high-speed air, forming a fine spray. Air pressure difference causes the fluid to move, and that's the key to carburetor operation. Let's relate the bug spray to a carburetor. The fuel bowl stores fuel, like fluid in the bug spray container. The nozzle is like the bug spray pickup tube. During the engine intake stroke, the piston moves down, creating low pressure in the cylinder and intake manifold. Atmospheric pressure outside the engine forces air through the carburetor to the low pressure area. Airflow past the carburetor nozzle also causes low pressure at the nozzle tip. Note that the fuel bowl is vented. Atmospheric pressure on fuel in the bowl and low pressure at the nozzle tip causes fuel to flow and mix with air flowing through the carburetor bore. The bore of the carburetor on the left is straight. It allows air volume, but velocity would be much too low for fuel flow. Remember, high-speed air is needed for fluid flow in the bug spray and also in carburetors. The carburetor on the right has a restriction in the bore called a venturi. Since the same amount of air entering the carburetor must exit, it must flow faster through the narrowest part of the venturi, and that's where the carburetor nozzle is located, the point of lowest pressure. In other words, as air velocity increases, vacuum or low pressure also increases. The changes in pressure are shown here. Note that maximum vacuum or lowest pressure is at the narrowest part of the venturi. Some carburetors have one venturi, others have two or more, and venturi size varies. But venturi size is critical to engine performance. Too small a venturi restricts airflow, affecting high speeds. If the venturi is too large, air velocity is lowered, affecting low speeds. For larger engines, either a 2 or 4 venturi carburetor is used. Each venturi is smaller in size than the single venturi carburetor, but total venturi area is greater. The small venturis provide high air velocity for low speeds, and the greater venturi area provides more air for high speeds. The carburetor meters air and fuel to meet engine needs by using 6 basic metering circuits. The float circuit supplies fuel to all metering systems. The choke enriches the fuel-air mixture for cold engine operation. The idle low-speed circuit provides the right fuel mixture for idle and low speeds. Power enrichment is for full load or high-speed operation, and the accelerator pump provides a rich mixture for sudden acceleration. We'll talk about each of these circuits, starting with the float. The float level affects the air-fuel ratio. If the float is too low, it leans the mixture. Too high makes the mixture too rich and may flood the engine. This close-up of the needle and seat shows that this is actually a fuel shutoff valve. As the fuel in the float bowl lowers, more fuel is permitted to enter the bowl from the fuel pump. Remembering that an air pressure difference is needed for fluid to move, the float bowl must be vented. As fuel in the float bowl lowers, the space above the fuel fills with air to maintain a constant atmospheric pressure in the bowl. Note that older model carburetors are vented to the atmosphere. Later model carburetors are vented internally for better emission control. The float affects drivability. Some typical float-related drivability symptoms are flooding, high or low speed surge, loss of power, fuel starvation, literally any symptom, whether at idle, low speed, cruise, high speed acceleration, or full throttle operation, especially during turns, can be caused by an improper float setting. Let's talk about the need for an idle low-speed circuit. When the throttle valve is almost closed, airflow is reduced, and air velocity is too low to cause low pressure at the carburetor nozzle. Hence, no fuel flows. Fuel must come from another source for idle and low speeds. The partly closed throttle valve restricts airflow, but velocity is high between the valve and the carburetor bore. Placing a hole at this low-pressure area, an idle port, and connecting this port to the fuel bowl will allow fuel to flow from high to low pressure into the carburetor bore. But there's more to the idle low-speed circuit. In operation, fuel flows through a metered pickup tube, the idle jet. At the bypass, air mixes with the fuel and flows through a restriction, the economizer. The idle bleed meters more air, and then the mixture is discharged through the idle port. You should know that most 2 and 4 Venturi carburetors have 2 low-speed circuits. During low-speed operation, the throttle valve exposes the transfer slot, and fuel begins to flow through the transfer slot as well as the idle port. When the throttle opens more, fuel flow increases until the main metering circuit delivers the fuel, usually between 30 and 45 miles per hour. This transfer should occur smoothly without fuel flow interruption. However, the float setting does affect the transfer point. If the float is too low, as shown here, fuel delivery through the main circuit will be too late and the engine could hesitate. If the float is too high, flooding can occur. Be sure to remember that idle settings are critical on emission-controlled engines. When performing this service, always use the technical service manual for idle speed and mixture setting procedures. Here we see some typical symptoms that may occur at idle or low speeds. Note that these symptoms relate to a hot engine. Cold engine symptoms are discussed later. Let's take a look at our next basic circuit, main metering. As throttle valves are opened and engine speed increases, airflow through the carburetor also increases. This increased airflow creates a low pressure in the venturi, and the main metering system discharges fuel. For main metering operation, some carburetors use a fixed jet with an air bleed, as shown on the left. Others use metering rods, as shown on the right. In the fixed jet type, fuel is metered in response to pressure differential by use of an air bleed. Since the pressure drop in the venturi is proportional to airflow, more fuel flows through the fixed jet at high speed than lower speeds. Looking at the metering rods, they are stepped or tapered to meter exact amounts of fuel. At idle, the largest section of the rod is positioned in the main jet, allowing fuel for idle or low speeds. As the throttle opens, the rod raises, positioning a smaller diameter in the main jet, allowing more fuel flow. The metering rod must be synchronized with the throttle valve. If the rod is too high, the mixture will be rich. If the rod is too low, the mixture will be lean. In a metering rod type main circuit, the proper fuel-air mixture during cruise and power enrichment is controlled by the position of the metering rod in the main jet. If a cruise surge occurs over 45 miles per hour, or if there seems to be a lack of passing power, the metering rods may require adjustment. This is a power enrichment circuit. It's controlled by mechanical linkage and engine vacuum. Metering rods provide more fuel for power enrichment. As the throttle opens, the decrease in manifold vacuum allows a spring to raise the metering rods. This permits more fuel to flow through the jets into the main well. When the throttle is at cruise, manifold vacuum stabilizes, allowing the metering rods to pull down to the proper point for the throttle opening. In most applications, a mechanical linkage positions the metering rods for the throttle opening. Vacuum further adjusts metering rod position in response to engine load. Power enrichment may also be accomplished by a vacuum power valve. When manifold vacuum is high, the power valve closes, limiting fuel flow. As vacuum lowers, spring pressure will open the power valve, increasing fuel flow. Vacuum power valves may be piston or diaphragm controlled. This type of power circuit is common to carburetors with main circuits that use fixed jets with air bleeds. Typical power enrichment circuit symptoms are a rough idle, which could be caused by an over-rich mixture due to a ruptured diaphragm. Poor high-speed performance could be caused by a too lean mixture or dirt clogging the power valve. Our next circuit is the accelerator pump. There are two types of accelerator pumps in use, the piston and the diaphragm type. When the throttle is opened suddenly to accelerate, airflow instantly increases through the venturi, but there's a brief time lag before fuel can overcome its own inertia and start to flow. This momentarily leans the fuel-air mixture. With a piston-type pump, as the throttle closes, an arm lifts the plunger, creating low pressure below the plunger. This allows the lower check valve to open and fuel enters the pump well. As the throttle opens, the arm pushes the plunger down, closing the lower check valve. Pump pressure forces the fuel to open the discharge check valve, and fuel discharges into the venturi. For even fuel flow, the spring on the plunger prolongs fuel discharge after linkage movement stops. This is a diaphragm-type accelerator pump. It operates similar to the piston pump. As the throttle closes, pressure on the diaphragm releases. A return spring pushes the diaphragm out, causing low pressure. The intake valve opens and a fuel charge enters the diaphragm cavity. When the throttle opens, the diaphragm forces fuel past the discharge check valve into the venturi. Accelerator pump service may be necessary if the engine stalls when it's hot or cold, or if it hesitates accelerating at low speeds. A good tip to remember is that if the engine coughs through the carburetor and the air horn looks sooty, the mixture is too lean. An over-rich mixture could cause the engine to lag or hesitate, but it won't cough. Now for the choke circuit. There are different types of automatic chokes, but they all perform the same function. When the engine is cold, a tightly coiled temperature-sensitive bimetal spring closes the choke valve, which reduces airflow to the engine. When the engine is started, manifold vacuum opens the choke valve a predetermined amount. As the engine warms up, the bimetal spring relaxes tension, allowing manifold vacuum to open the choke valve. When the engine accelerates during the warm-up period, manifold vacuum drops and slightly closes the choke valve. Since the choke valve is pivoted off-center, incoming air pressure partially opens the valve, allowing the engine to breathe. This is the automatic choke cover. It houses the temperature-sensitive bimetal spring. Adjusting this cover controls the length of time the choke will operate. It does not lean or enrich the fuel mixture. Bimetal spring tension may be controlled by engine heat, either from air heated by the exhaust manifold or by heated engine coolant. Bimetal spring tension may also be controlled electrically. This type choke does not use engine heat. Instead, current from the alternator heats the bimetal spring. A special heating element controls the rate of heating. When the temperature is low, only the center element heats. When the engine approaches operating temperature, both elements heat up the bimetal spring to relax tension at a faster rate. A third type of automatic choke is the part electric, part engine heat. It's called an electric assist choke. In operation, hot air from the exhaust manifold heats the bimetal spring. Alternator current assists in heating for faster choke release after the choke cover interior approaches operating temperature. When the engine is shut off, the thermostatic switch stays closed until the interior temperature of the choke cover lowers as in a cold engine. In operation, the choke is set by depressing the accelerator and releasing it. The fast idle cam linkage is positioned by the choke valve opening. The choke unloader mechanically opens the choke valve to clear a flooded engine. Depressing the accelerator to the floor and holding it there while cranking should clear the engine. To service the choke, always make adjustments in this order. Call it 5 steps to a happy choke. First, adjust initial choke clearance. Second, adjust the fast idle linkage. Third, adjust the choke unloader. Step 4 is the choke cover, and Step 5 is adjusting fast idle RPM. Each of these adjustments relate to correcting drivability symptoms. Let's start with Step 1. Setting initial choke valve clearance is the most important step in choke service. Improper adjustment will cause all other choke settings to be off. Typical symptoms relating to improper initial choke valve clearance are the engine loads up, stalls, or idles rough. Here we should note the 2 different methods used to set initial choke valve clearance. The first is the piston pull-off. Note that manifold vacuum draws the piston against bimetal spring tension. The position of the piston controls the choke valve opening. The second method is the diaphragm type pull-off. Like the piston pull-off, vacuum is used to pull against the bimetal spring, controlling initial choke valve clearance. Adjusting the fast idle linkage is performed only after setting the initial choke valve clearance. If this linkage is out of adjustment, the engine could idle too fast and too long, or too slowly for too short of a time. The choke unloader is always set at wide open throttle. An incorrect setting will not permit clearing a flooded engine. Adjusting the choke cover controls the operating time of the choke. It does not affect idle speed. Typical symptoms that can be corrected by properly setting the choke cover are a choke that stays on too long or too short of time, or engine stalling after a short warm-up, but not after it's hot. Fast idle speed is always adjusted after the engine reaches operating temperature. An improper adjustment can cause the engine to idle too slow when cold, race during warm-up, or stall. When performing choke service, remember that adjustments differ between carburetor models. Specific adjustment procedures are explained in the service charts included with this film release and in the technical service manuals. To summarize, all carburetors essentially work the same way. They meter air and gasoline to meet engine needs, and carburetors operate on air pressure difference. Fuel flows from high to low pressure areas. Also, all carburetors have these 6 basic metering circuits. However, some carburetors with metering rods combine main metering and power enrichment in a single circuit. For quick drivability symptom diagnosis, we can use graphs to show how each carburetor fuel metering circuit responds to engine demands. Starting with the float or fuel inlet system, you'll see that the float is used to constantly supply fuel to all the fuel metering systems. The choke temporarily enriches the fuel-air mixture, which aids in starting and running a cold engine. On this portion of the graph, we see that the idle or low-speed circuit provides the proper fuel mixture for idle and low-speed engine operation. A rich mixture is used for smooth operation and prevents random misfire caused by a too lean mixture. On our graph, note that the main metering system provides an economical fuel-air mixture at cruising speeds. And here we see that for high-speed or full load operation, the fuel-air mixture must be enriched to gain increased engine power. Although not shown on the graph, the accelerator pump overcomes lag with an extra shot of fuel. Make it a point to remember that drivability symptoms can involve more than the carburetor itself. The entire fuel system, the ignition system, emission devices, and the condition of the engine all have an effect on drivability. In this film, we have reviewed the basic fuel system, from fuel tank to carburetor theory and symptoms. When servicing any fuel system component, always use your technical service manual. It will help you isolate problems and identify the proper service procedure. Heavy emphasis has been placed on carburetor theory and drivability symptoms. To aid you in servicing specific AMC Jeep carburetor models, 2 special flip chart type booklets are included in this film release. They show in step-by-step photos how to disassemble, adjust, and reassemble a specific carburetor. It's a good idea to use them under the hood or on the bench.